Have you ever, looked at your phone or maybe some complex hardware and just wondered how it all works together? How all those bits inside manage billions of operations a second without, well, getting completely tangled? If that sounds familiar, then today's deep dive is definitely for you. We're going to try and cut through some of that complexity, give you a real shortcut to understanding something called the Advanced Extensible Interface, or AXI Protocol for short. Think of it like the nervous system of the digital world inside these devices.
That's a really good analogy, actually. AXI is, well, it's pretty much become the backbone for modern system-on-chip designs. It's like a whole computer on one tiny piece of silicon, and also for FPGAs, those field-programmable gate arrays you can configure. It came from ARM, part of their AMBA standard, and a huge reason it's everywhere is because it's royalty-free. It's real genius, I think, is how it simplifies hooking together all these different complex parts.
Right. So the big question we want to tackle today is how do these incredibly fast, incredibly complex pieces actually talk to each other without it just descending into chaos? Our mission, then, is to unpack the core communications signals, those terms you hear a lot, valid and ready, and then dig into this really crucial concept called backpressure. Sound good?
Sounds great. Let's do it.
Okay, so AXI. Fundamentally, what are we talking about here? Is it like an old school computer bus, or is it something else?
Yeah, good question. It's quite different, actually. At its heart, AXI defines direct point-to-point connections. Imagine a dedicated phone line. It's between a component called a manager, that's usually the master, like a processor starting things off, and a subordinate, or slave, like memory responding. This direct connection idea is what really sets it apart from older shared bus architectures. It maximizes the available bandwidth because the path isn't shared.
And that must be a huge reason why it's so widely used then, that direct line.
Oh, absolutely. It makes putting together different IP modules much, much easier, less design effort, faster cycles, and importantly, it simplifies verification too. AXI is built for speed, high clock frequencies. It has things like separate read and write channels. It can handle multiple requests being out at the same time, multiple outstanding addresses, and it can even complete transactions out of order. All of that is designed to push bandwidth up and latency down, which you absolutely need these days.
I've heard it called the digital highway from AR. That paints a picture of pure speed, doesn't it? But how accurate is that? Is it just wide open road?
Yeah, the highway metaphor captures the bandwidth part, sure. But thinking of it as just a simple free-flowing road isn't quite right. It's probably better to think of it as a really sophisticated traffic control system. The rules, signals, ways to manage jams, that congestion management. That's basically what backpressure is. So, yeah, AXI allows for high performance, but getting that performance means you need smart drivers, the manager and subordinate components, and efficient traffic control, the interconnect logic itself. Even highways get gridlocked without good management.
Right, okay. A smart highway. Makes
Yeah.
sense. And like any sophisticated system, I guess there isn't just one single version of AXI. What are the main flavors people run into?
That's correct. There are a few key variants tailored for different jobs. First up is AXI4, sometimes called full AXI. This is the high-performance powerhouse, mostly for memory-mapped stuff. It supports these things called burst transfers, up to 256 basically 256 chunks of data in one go. Very efficient. AXI4 also has features like quality of service, QoS signals, so you can prioritize important data like maybe video over less critical stuff. And it supports reordering transactions too.
Okay, the heavy hitter. What else?
Then you got AXI4 Lite. Think of it as the simplified version. It's great for lower speed communication, typically when you just need to access control registers or status registers and peripherals. Its main characteristic is single beat transactions, just one data transfer at a time. Much simpler to implement.
Makes sense for simple console stuff. And the third one?
The third one is AXI4 Stream. This one's different again. It's optimized purely for unidirectional high-speed streaming data. Think video pipelines, digital signal processing, fast network data. The key thing here is it doesn't have address channels. It's all about just moving data, either continuously or in bursts. Very streamlined for pure data flow.
Okay, so just to summarize for everyone listening, AXI4 is the big gun for high-speed memory access with bursts. AXI4 Lite is the simple, single-shot version for control. And AXI4 Stream is the specialist, just for pumping data streams fast, no addresses needed.
Got it. Now, let's really zoom in on the magic, the core handshake, these valid and ready signals. How do they actually coordinate things? It's actually quite elegant in its simplicity. You have the valid signal. The source, the sender, asserts this, puts it high, to basically say, hey, I've got valid data right here for you.
Yeah.
Then you have the ready signal, the destination. The receiver asserts this one to say, okay, I'm ready, send it over. And the actual data transfer, the handshake, happens exactly on the rising edge of the clock, but only when both valid and ready are high at the same time. It's a mutual agreement.
Simultaneous, yes.
Exactly. So, like on the right address channel, the manager asserts valid, the subordinate asserts are ready. Boom, address transferred. On the read data channel, the subordinate asserts valid, manager asserts are ready. Boom, data received.
Seems logical. But I hear there are some really strict rules about how these signals behave. What are those rules of engagement?
Ah, yes, the rules. There are 4, and they're absolutely critical. Rule number 1, the source cannot wait for ready to go high before it asserts valid. This might seem a bit weird, it's asymmetric, but it's genius. The sender must signal valid as soon as it has data, period. It doesn't wait for the receiver. Why?
Okay, why?
Because if both sides waited for the other to signal first, you could get stuck forever, right? A deadlock. This rule guarantees that communication always has a chance to start. It ensures system liveness.
Ah, clever. Prevents a standoff. What's rule 2?
Rule number 2, the destination can wait for valid to be asserted before asserting ready. This makes sense, right? The receiver only needs to say, I'm ready, when there's actually something valid being offered. It stops it from grabbing garbage data.
Okay, and rule 3?
Rule number 3, this one's super important. Once asserted, valid must stay asserted, we call it sticky, until the handshake happens, when ready also goes high. This sticky valid is key. If the receiver isn't ready, ready is low, the sender just holds valid high, waiting. That stalling forced by the destination, that is backpressure. So you see, backpressure isn't some extra feature. It's baked right into the handshake because of this rule. It's how the system naturally handles slowdowns without losing data.
Wow. Okay, so back pressure is just inherent, built in. And the last rule?
Rule number 4. The ready signal can be asserted or deasserted whenever the destination wants. It has full control over saying, I'm ready or hold on. But there's a catch. If ready is high on that clock edge and valid is also high, the transfer must happen. The destination is committed at that point. It has to take the data.
Right. It can change its mind before the handshake, but not during.
Precisely.
So these rules allow for those common handshake scenarios, don't they? Like ready before valid the fast path, destination is ready, source sends, done in one clock cycle.
Yep, the most efficient case.
Then valid before ready, which is the classic stall or back pressure example. Source is ready, destination isn't, so valid just sits there until ready comes high.
Exactly. That illustrates the stall.
In simultaneous assertion, where they both go high together and the transfer just happens immediately.
Correct.
Yeah.
All enabled by those 4 simple rules.
Okay, so to handle all this efficiently, AXI doesn't just use one single pathway for everything, does it? Tell us about these channels. Why are they so important?
Right, yeah. The multi-channel architecture is key to AXI's performance. In the main variants, AXI-4 and AXI-4 Lite, you typically have 5 distinct independent unidirectional channels. There's the write address channel, or AW master sends the write address here. Then the write data channel, W master, sends the actual data. There's also a signal here called WLEs that marks the end of a burst of data. Then the write response channel, B. This is where the subordinate sends back a status like, okay, write complete. Then you have the read side, the read address channel, AR master sends the read address, and finally the read data channel, our subordinate sends the requested data back. And similar to write, there's an RLEAS-T signal to mark the end of a read burst.
5 separate channels. And the crucial part is that they're independent, right? Each with its own valid ready pair.
Exactly. That independence is vital. It means if, say, the write data channel gets stalled because a buffer is full, it doesn't block the master from sending a new address on the write address channel or doing reads on the read channels.
Ah, so things can happen in parallel. It encourages pipelining.
Precisely. It allows for a really high degree of concurrency. A master could be sending a new read address while the slave is still busy sending back data from a previous read. This keeps the bus utilized much better and helps hide latency, especially if you're talking to something slow like off-chip memory. And from a practical standpoint, it also makes debugging a bit easier because you can often isolate problems to a specific channel.
Okay, that makes sense for AXI-4 and Lite. How does AXI-4 Stream fit in, being channelless, essentially?
Well, AXI-4 Stream simplifies things dramatically for its specific purpose. It basically just has one unidirectional channel for the data itself. The core signals are just TL at source has data, ready destination is ready, and T data, the actual data payload. It does have useful optional signals too, like TLST, which is really important for marking the end of a packet or frame, say in networking or video, and TOSR for carrying extra sideband information like maybe video sync signals. But fundamentally, it's one data byte.
Got it. Which brings us back full circle to back pressure. You said it's fundamental, inherent. We need to be clear. This isn't automatically a bad thing, is it? It's a necessary control mechanism.
Absolutely, 100%.
Mm.
It's easy to hear pressure or stall and think it's a problem, but back pressure is just the natural resisted flow of data. In AXI terms, it's simply what happens when the source asserts valid, saying, I have data, but the destination keeps ready low, saying, I can't take it right now. This forces the source to wait. That's back pressure. It's flow control.
So why is it so essential? What catastrophic things does it prevent?
Oh, several critical things. Firstly, resource contention. If you have multiple masters trying to talk to one slave, back pressure is how the interconnect or the slave manages who gets access and when, preventing chaos. Secondly, varying processing speeds. You almost always have faster components talking to slower ones. Back pressure stops the fast guy from overwhelming the slow guy, which would just lead to lost data. Thirdly, it's absolutely crucial for clock domain crossings, or CDCs.
Right, when parts of the chip run at different speeds.
Exactly. Moving data reliably between those different clock speeds is tricky. Back pressure, via the handshake, provides the synchronization needed to do that safely without corrupting data. And maybe the most intuitive reason, preventing buffer overflows. Receivers have limited storage, right? Buffers. Without back pressure, a fast sender could just keep pouring data in until the buffer overflows and poof, data is lost. I like the chocolate factory analogy. It's way better to signal back to the machine, making the chocolates the sender, to slow down, rather than hoping the person packing them, the receiver, can somehow magically keep up, or letting chocolates pile up and fall on the floor.
Slow the source, don't overflow the sink.
Precisely. It also simplifies slave design sometimes, because the slave knows it can just hold off asserting ready until it's truly ready to process the incoming data or address.
And you said it's that sticky valid rule number 3 that really makes this work.
Yes, exactly. The fact that valid must stay asserted until the handshake completes, combined with the destination having full control over ready, is the implementation of back pressure. The source is forced to wait if ready is low. It's built right in.
Okay, but nothing's free. What's the cost? Does back pressure hurt performance?
It definitely can, yes. It's a trade-off for robustness. The main impacts are on throughput and latency. For throughput, obviously, if the source is stalled waiting for ready, no data is moving during those clock cycles, so your effective data rate goes down. But interestingly, sometimes allowing back pressure can actually help overall system performance. It lets you design components for their average data rate, using buffers to handle peaks rather than having to over-design everything for the absolute worst-case peak, which can be wasteful. Some studies show you might even use a slightly slower clock and maintain throughput by managing flow well.
Huh. That's counterintuitive, but makes sense. And latency.
For latency, yes, back pressure adds delay to individual transactions. The start of the transfer is pushed back. But crucially, it's a controlled delay. It prevents catastrophic failures like buffer overflows, which would cause much larger unpredictable delays and data loss. And AXI has ways to mitigate this latency impact, like allowing multiple transactions to be outstanding and completing them out of order. So even if one transaction is stalled, others can potentially keep moving.
Okay, so looking at the memory-mapped versions, AXI4 and Lite, how does back pressure play out across those 5 different channels? Is it everywhere?
Pretty much, yeah. It can happen on any channel where the receiver isn't ready. On the write address AED channel, the slave might deassert ready if its internal queue for address is full or it's just busy. So the master has to wait to send the next address. On the write data W channel, the slave deasserts ready if its data buffer is full. The master stalls sending write data. On the write response B channel, this is the other way around, the master might deassert ready if it's not ready to process the write completion signal. Maybe its internal response queue is full, so the slave has to wait to send the OK.
Ah, so the master can apply back pressure too.
Yes. And similarly for reads, on the read address AR channel, the slave deasserts ready if it's busy or can't accept another read request yet. And on the read data R channel, the master deasserts ready if its buffer for incoming read data is full, or it's just not ready to consume the data yet. So the slave has to wait before sending the data.
So you could have a situation where a master is, say, happily accepting read data from one fast slave, but it's holding off already applying back pressure to another slower slave it's also reading from.
Exactly that scenario. And this is where transaction IDs become absolutely essential. Remember those AWID, ARID, BEAD, RID signals?
Right, to tag different requests.
Yes. And AXI allows out-of-order completion. So if a read transaction with ID 5 gets stalled because the master isn't ready, where ready is low, A different read transaction, say with ID 6, maybe going to a faster part of memory, can still complete and return its data. The master uses the RAD on the read data channel to match the incoming data to the original request. This ability to let other transactions proceed while one is stalled is huge for performance. It helps hide the latency of the stalled transaction by keeping the bus busy with other work.
But that sounds like it adds complexity for the master, keeping track of all those IDs and out-of-order responses.
It absolutely does. The master needs logic to manage outstanding transactions and match responses correctly, and verification gets much harder too, testing all the possible interleavings.
And what about bursts? If backpressure happens mid-burst, does the whole thing stop?
Yes. If a slave deasserts ready during a write burst, for example, the master has to stall the entire burst at that point. The W of the LED signal for the current data beat stays high, the data stays stable, until ready comes back high and that handshake completes. Then the burst continues from where it left off. Those W last and RL last signals are key here too, telling the receiver when the very last beat of the burst is being transferred, even if there were stalls along the way.
Okay, makes sense. Now let's switch to AXI 4-stream, designed for pure speed, continuous flow. How does backpressure work there?
It's fundamentally the same handshake. TVLID from the source, TREDI from the destination. If the destination lowers TREDI, the source must stop sending. It has to keep TVLAD high and the current T data stable until TREDI goes high again. So stalling happens just the same way. And there's really no built-in limit in the protocol itself on how long a destination can keep TREDI low. It can stall for as long as it needs to.
But you mentioned earlier that TREDI can be optional in AXI 4-stream. That sounds risky. What happens if it's just left out or tied high permanently?
Ah, yes. This is where AXI 4-stream gets really interesting and potentially dangerous if you're not careful. If you omit TREDI or tie it permanently high, you effectively have zero backpressure support. The destination loses its ability to say stop.
So the source just sends constantly.
Sends constantly. This kind of setup is usually only seen with fixed-rate components, things that absolutely must produce or consume data at a specific non-stop rate, maybe like a direct connection to a high-speed DAC or ADC. In those cases, if you did have TREDI and it went low, you'd inherently be dropping data because the source or sink physically can't stop.
But outside of those very specific cases, ignoring TREDI sounds like asking for trouble.
It really is. Without TREDI, data loss from buffer overflows becomes highly likely if the destination ever falls behind the source's pace, even momentarily. Sure, omitting TREDI might simplify the logic superficially. Some might say it makes AXI stream barely more than just naming conventions for signals. But in any kind of pipeline where different blocks process data sequentially, losing that flow control can make life, as one designer put it, 100 times more complicated. If one block stalls unexpectedly and can't signal back up the chain, you can get catastrophic errors propagating through the whole system.
So the resource cost of implementing TREDI, maybe with a small FIFO buffer, is often worth it for the robustness it provides.
Generally, yes. Using the full ASI 4-stream handshake with TREDI allows you to design for average data rates, letting buffers absorb the peaks. This is often much more resource efficient and reliable overall than trying to build a perfectly lockstepped, fixed-rate system where any hiccup causes data loss.
And how does TLS, the end-of-packet signal, interact with this optional flow control?
TLS is super important for packetized data. It signals the final beat of a packet or frame. Critically, it follows the exact same TVLID TREDI handshake rules as T-data. This means if backpressure happens, TREDI goes low. Right when T-last is being sent, TLast and the final data beat will just be held stable until TREDI goes high again. This ensures that packets are always transferred completely, even if they get stalled mid-transfer.
We've covered a huge amount here. Thinking practically now for the designers listening, how do they actually manage all this? How do they use backpressure effectively and design for performance and reliability?
Well, a key strategy is intelligent buffering. As we touched on, FIFO's first-in, first-out buffers are your best friend. You use them to decouple different stages in a processing pipeline. They absorb those temporary mismatches in data rates. The downstream block can apply backpressure to the FIFO, but the upstream block can keep sending data until the FIFO is full. It smooths everything out. There are also things called skid buffers. These are usually very shallow FIFOs, maybe just 1 or 2 entries deep. Their main job is often to break long timing paths specifically, combinational paths between the ready signal of one block and the valid signal of the next. Putting a register stage in there helps the design meet timing at higher clock speeds.
Okay, buffering helps manage flow. But what about preventing total system meltdown? Deadlocks.
Right, preventing deadlocks and live locks is paramount. A deadlock is when components get stuck waiting for each other in a circular dependency, and nothing moves forward. A live lock is slightly different. Components keep changing state, maybe responding to each other, but make no actual progress. We already mentioned that AXI's asymmetric handshake rule, source doesn't wait for ready, prevents one common type of deadlock. But complex systems, especially with multiple masters, slaves, and interconnects, can still have subtle deadlock possibilities. Preventing them requires really careful design and critically rigorous verification. Using formal verification methods and building extensive simulation test suites, especially with randomization, is essential to hunt down these corner cases.
So assume you've avoided the deadlocks. How do you then push the performance? Squeeze out every last drop.
Several levers to pull. Obvious ones first. AXI data width. Using a Weiger bus, like 64-bit or 128-bit instead of 32-bit, moves more data per cycle. Simple but effective. AXI burst length. Using longer bursts, especially in AXI4, up to 256 beats, dramatically reduces the overhead of sending the address for each transfer. Big impact on efficiency for large data moves. Then, using quality of service, QoS, signals in AXI4. This lets high-priority masters get preferential treatment through the interconnect, ensuring critical tasks meet their deadlines. Pipelining is also key. AXI's channel structure inherently supports it. Overlapping operations fetching the next address while the current data transfers improves throughput. But you have to be careful not to add too much pipelining, as each stage adds a little latency. And of course, leveraging those core features like multiple outstanding transactions and the independent read-write channels is fundamental to keeping the highway busy.
And inevitably, things will sometimes go wrong during development. How do you debug these complex beasts?
Debugging AXI interactions can be tricky, yeah. Common problems are handshake violations, breaking the rules, ID mismatches causing data corruption, unexpected stalls, creating bottlenecks, that kind of thing. Your toolkit includes protocol checkers. These are often IP blocks you can instantiate in your FPGA design that specifically monitor AXI interfaces and flag any violations of the spec. Super useful. Then you have waveform viewers in simulation and logic analyzers for on-chip debugging, like the Vivado ILA. These let you actually see the valid and ready signals toggling, trace transaction IDs, measure throughput, and pinpoint exactly where stalls are happening. Indispensable. And for pre-silicon verification, simulation frameworks like UVM, Universal Verification Methodology, are the standard. They allow you to build sophisticated test benches that generate constrained random stimulus, monitor all the channel handshakes, check data integrity using scoreboards, and really stress test the design under corner case conditions. Sometimes designers also add extra FIFOs or register stages purely for debug visibility, or use software running on an embedded processor to drive specific AXI transactions for testing.
Wow, okay, what a journey. We went from the basic valid-ready hello through the multi-lane highway of channels and navigated the necessary traffic jams of backpressure across all the AXI flavors. It's really clear now just how foundational this protocol is for making modern high-performance chips and FPGAs actually work reliably.
Absolutely. Understanding how AXI manages data flow, especially backpressure, is just non-negotiable for anyone designing serious hardware today. It really comes down to smart use of buffering like FIFOs and skid buffers, being really careful about avoiding deadlocks, and then using all the performance features AXI offers to optimize the system.
So for everyone listening, maybe the next time you use your phone or any smart device, take a second to think about those invisible digital handshakes happening billions of times a second inside. That sophisticated traffic control system, AXI, managing the flow, applying back pressure when needed. Now that you understand a bit more about that intricate dance, how might that change the way you think about the seemingly smooth operation of all the technology surrounding us? Something to ponder.